All right, so obviously we learned how to do nodal analysis in EE220, one of the simpler types of problem-solving mechanisms for DC circuits. Actually, it just so happens that we basically used nodal analysis in the previous video too. This method here of using KCL to find the unknown value of Vx is basically exactly what we're going to do in this problem. Just real quick, I'm going to brush over the steps and then I'll go right into the example. The first thing we do is we determine which nodes in the circuit have unknown voltages, and how many nodes in particular. Then we label all the currents and into and out of each of those nodes, and we write a KCL expression for each of those nodes. So this works, generally for any number of node voltages you're trying to find, and then you can go ahead and solve the resulting system of equations to obtain all the unknown node voltages. I just kept it pretty simple so that we don't have to do too much work solving these differential equations. It's quite tedious to do that by hand. But after we write the KCL expressions for each node, we use Ohm's law and we substitute voltages and resistances into our KCL expression so that all we're left with is the system of equations that we can then solve to obtain the unknown node voltages. Okay, so kind of a mouthful, but this is just review. I don't really want to spend too much time on it, but let's just set up the problem kind of on this slide. What I want to solve is I want to give a problem with a sinusoidal source Vs of t. I'm going to put a 1 nanofarad capacitor here, 50 ohm resistor to neutral here, and then I'll put another 50 ohm resistor here, and a 1.6 microhenry inductor right here. And so we can label our three nodes. Let's just call them Vx of t, Vy of t, and Vz of t. Those are all our unknown voltages, right? We just took care of the first step. I guess Vx of t isn't really unknown because it's just going to be equal to Vs of t. But let's say that the problem here asks us to solve for Vy of t. So that's all we're interested in. So that's the one that we want to determine. Okay, so the next step is to label all the currents into and out of that node. So we need to label the current in, which is going to be I1. The currents out are going to be I2 and I3, of course. So you can see how very similar this is to the previous problem. And then it says to write a KCL expression for each node from 1. Well, before we do that, let's go ahead and convert this guy over to the phasor domain. I haven't given any parameters for Vs of t yet, so let me do that. Vs of t is going to be 3.3 times the sine of 2 pi times f, which in this case I'm making 5 megahertz times t volts. Okay, so 3.3 volts at 5 megahertz. We know that that phasor is just going to be 3.3 angle 0 degrees volts. We have no phase shift on our input source. Okay, so when we go to the phasor domain, my sinusoidal source is basically just going to be 3.3 angle 0 degrees. I've got a capacitor whose impedance I'll need to find. I've got a resistor. I know that that's just going to stay 50 ohms. I've got another resistor that's going to stay 50 ohms. And I've got an inductor whose impedance I'm going to need to find. Okay, so this is me getting ready to set this problem up to do the KCL. Of course, I1 is going to flow here, I2 there, and I3 here. But we still need to determine our impedances for our capacitor and our inductor. So let's go ahead and do that. For the inductor first, which is pretty easy, it's going to be j omega L, right? This impedance is j omega L, which I'm going to find right now using my calculator. It is going to give me, let's see, oh, sorry, I have an error in my calculator. Let me just delete that, and there we go. So for my inductor, I get 50.265. So let's just say J 50.3. How about that? And then for my capacitor, I get basically minus J times 10, or sorry, is that what it is? What did I do wrong here? Oh, interesting. I have an error in my calculator. Okay, there we go. Sorry about that. Huh. I don't know what I did wrong. Okay, I have an error somewhere. Let me go ahead and stop this video.